Hello and welcome to the Mathematical Ramblings channel, where we look at interesting math topics, the ideas behind them, and the story of the characters who actually made these discoveries. And we'll start off with how Archimedes worked out an estimate for pi to within 0.07% over 2,000 years ago. We'll look at how he did it, and then we're going to use a somewhat similar method to work out pi to an even better degree of accuracy. And quickly, before we move on, if you could hit the subscribe button and the notification bell so that you're notified of any future videos, that'd be greatly appreciated. Thank you. To start off with, we need to actually define pi and know what pi exactly is. Most people know that pi is related to circles, and it is. We'll quickly sort of look at the parts of the circle, just as revision. So the circumference of the circle is the outer perimeter, it's that length. The radius is the length from the center of the circle to the circumference of the circle, and the diameter, sort of two connected radiuses. Technically, it's a line that goes from one point in the circumference to the opposite point that also passes through the center. Pi is actually defined as the ratio between the circumference and the diameter. So, in another way, it's pi is equal to circumference over the diameter, and this can be rearranged to get the well-known c equals pi d. So that's the relationship between the circumference and the diameter, and it's constant. We can also say that the diameter, as I'd explained, is sort of two radiuses. It's you can see it visually, it's sort of intuitive, they're sort of connected. And if you substitute this into c equals pi d, we get that c is equal to 2 pi r. We can then go from this and show that a is equal to pi r squared. That's something that Archimedes also did 2,000 years ago. And you can also use sort of modern calculus, but anyway, that's a topic for another video. Using a equals pi r squared, this is probably one of the most well-known things about a circle, we can rearrange to get that pi is equal to a over r squared. And that's quite important, because if we can work out the area, not in terms of pi, then we can work out an estimate for pi. So for example, we could use a hexagon, and you can see that the hexagon takes up a lot of the area of the circle, and we can work out the area of the hexagon fairly easily. It doesn't take up all the area of the circle, but it's a good amount. The key thing with the hexagon is that it's inscribed. Now, an inscribed hexagon, or an inscribed polygon for that matter, is one where all the points on the hexagon touch the circumference of the circle it's within exactly, such that the hexagon is fully contained within the circle. So that's shown here. We could increase the number of sides of this polygon, so we could use a dodecagon, and you can see that the dodecagon takes up a lot more of the circle. There's only sort of a few white bits where the circle, part of the area of the circle, isn't also part of the dodecagon. And we can keep on adding, and what Archimedes eventually went up to was the final boss of polygons, also known as the n-Gon hexagon, and that's a 96-sided shape. It's a lot of sides, and it's so many in fact that it really does look almost like a circle. If you saw that and you didn't know it was an n-Gon hexagon, you probably would think it's just a circle. And that means that it's going to be a really good approximation for pi. Obviously it's not perfect, but it did allow Archimedes to work it out to within 0.07% 2,000 years ago, which is really impressive, to be honest. Moving on with Archimedes, obviously he was the inspiration for this video, so I thought it'd be interesting to look a bit more about who exactly he was. Most people know that he was an ancient Greek mathematician, but to be more specific, he was born in Syracuse in the Isle of Scilly, not the Isles of Scilly, but the island of Scilly in Italy, in 287 BCE. He's probably even better well known though for, to be honest, the Eureka. So the story goes that he was in the bathtub. He obviously, being in the bathtub, he displaced some of the water, and he realized this. And his realization was that the water that he displaced caused a sort of resistant buoyancy force. Anyway, they call it the Archimedes principle. I won't go into details in this video, but anyway, he sort of jumped out of his bathtub, ran down the street, shouting Eureka, meaning I have it in Greek. But yeah, that's probably what he's most well known for. As I said, he obviously was a pure mathematician, so he developed sort of beginning ideas of calculus, and using this he proved that the area of a circle was pi r squared, or an equivalent sort of expression. But he was also an applied mathematician, so he was an astronomer, an engineer, and also of course with the Eureka moment involved with sort of fluid dynamics and stuff like that. Moving on to be more specific with this video, he worked out an estimate for pi, and he used that using a combination of inscribed polygons, which we've already looked at, and something else, sort of the opposite, called circumscribed polygons. And you can see here that instead of the hexagon being within the circle, the circle is within the hexagon. And what that means is that the center of each edge of the hexagon touches the circumference exactly, as shown here. And obviously that can be extended for any other polygon. And what he did was find the perimeter, instead of finding the area, which we'll do, he found the perimeter of the inscribed hexagon and the perimeter of the circumscribed hexagon. He found the averages of the two, and he used that to work out an estimate for pi. And of course he increased the number of sides of the shape, so he went up to a 96gon. So he found the perimeter of an inscribed 96gon and a circumscribed 96gon, found the average, and used that to work out an estimate for pi. And also, if anyone knows where exactly this icon is from, write it down in the comments, and well done if you do get it right. We'll start off with the maths part, of course, by looking at the area of a hexagon. Now, a regular hexagon, if you didn't know, can be split into 6 identical equilateral triangles, so as shown here. And it's fairly easy to work out the area of a triangle. Most people know that the area of a triangle is half base times height, the vertical height, but that's a little more annoying here. We could use the Pythagoras theorem, but there's a simple alternative, and that's to use that A is equal to half AB sine C. Now, if we focus on just sort of one triangle, that one here highlighted in purple, then that's what A and B represent the lengths of the two adjacent sides, and C represents the angle between them. Now, what actually are these values going to be? Well, A and B, those lines are both radii of the circle, so they're going to be radius. They're going to be the values are going to be the radius length, and then the angle between them is actually going to be 60 degrees, because in an equilateral triangle, all the angles are 60 degrees because it's a regular shape, and then 180 degrees in a triangle. So we can swap out those values and substitute to get that the area of one of these triangles is half r squared sine 60. Now, having the r squared there is a bit annoying, so what we can do is substitute 1 into r. It's still fully valid, and that simplifies calculations later on. So moving on, the area of one of the triangles where you have a radius of 1 for the circle is half times 1 squared times sine 60, and that's just half sine 60, and that's root 3 over 4. We can then multiply by 6 because there are 6 triangles in the entire hexagon, and that will give us that the area of the entire hexagon is 6 times the root 4. That's about 2.598. The final step is to actually look at why this is an estimate for pi. So we know, as you probably know, A is equal to pi r squared. Talked about that earlier. And we know here that we've set the radius to be 1. So we can simply say that the area of the circle is equal to pi times 1 squared. Because of this, we can say that the pi is equal to the area of the circle, and we know that the area of the circle is approximately, very approximately in this case, equal to the area of the polygon. So because obviously, of course, the hexagon takes up a lot of the area of the circle, so they're going to be approximately equal, the areas. And because of this, we can say that pi is approximately equal to the area of the hexagon, which is 2.598. And that's not a great estimate, but we can do a lot better by increasing the number of sides. Now, instead of just looking at like a higher sided shape, a higher number of sided shape, like a dodecagon or even an aecontohexagon, I thought it'd be easier or more interesting to look at it in a more general way. So if we think about an n-Gon, that's a shape with n sides. Now this is a decagon, but the idea is that you have a regular polygon with n sides, and we want to work out the area of that polygon. So what we could do, the easiest way to do this, is actually to split that polygon into triangles, and the number of triangles is going to be equal to the number of sides, which makes sense. So here we have the dodecagon, 10 sides, so 10 triangles. Now we want to work out the area of each of these triangles. Again, we can use A equals half AB sine C. We focus on a single triangle. The lengths of the triangles, again, they're going to be 1, because that's what we set the radius to be, and there's going to be an angle between them. Now, it's not necessarily that obvious immediately what this angle will be, so we'll leave that for now. We'll say that it's equal to half times 1 squared times sine y. That's just substituting again. What we can then do is actually work out what this angle is. So we said it was y, it's actually just 360 over n, and if you think about it, it makes more sense. So around a point, there are 360 degrees. And if we have n triangles around a point, then each of those triangles will have an angle of 360 divided by n. So if we substitute this now, we get that the area of one of these triangles, given n as the number of sides of the polygon, is equal to half sine 360 over n. But this is only a single area of a single triangle, so we need to multiply by the number of triangles, which we've already said is n, and that will give us half n sine 360 over n. Finally, I thought it would be interesting to actually look at some values. So starting with the final boss of polygons, the n-Gon hexagon, the area of a 96-gon is half times 96 times sine 360 over 96. So this is as far as Archimedes went, and that's 3.139 to 4 significant figures, and that's pretty good actually. He didn't use this method, as I said before. He used the perimeter and more of an iterative process with geometry, but he would have gone to the same result. And that's within 0.07% of pi, so that's a pretty good estimate considering how long ago it was. And really, it's sort of good enough for now, really. You could use that, it's not that far off. And just sort of looking arbitrarily a high number of sided shape, then we could look at 1,000-sided shape, and I do not want to imagine what the name of that shape is, even if it exists. It's the final form. So that would be 3.141578983, and that's quite a lot better than our original hexagon. It's 4 decimal places. Actual pi is about 3.1415926. This is 3.1415, so it gets those first 4 decimal places right. And of course, we could keep on adding more sides to the shape. We could get up to a million, billion, trillion, tree 3, Graham's number, all of those sided shapes, and that's going to be a lot better estimate for pi. So this is one way of working out more decimal places of pi. It's not necessarily the most efficient way, but it is a way of working out a good estimate for pi. So I thought it would be interesting as well to look at this graphically, just so it's sort of easier to understand. We have 2 graphs, or 2 lines here. We have the blue line, that's y equals pi, and the red line or curve, that's half x sine 360x. So that's probably familiar. It's exactly what we just used. It's half, before we had the area of the polygon was half n sine 360 over n. We just sort of swapped out n for x here. So as we increase the x value, you can see that this red line gets closer to the blue line. And that means that as we increase the number of sides on the circle, or the number of sides on the polygon, then we get a much better approximation for pi. So you can just see that red line getting much closer. It will never actually reach the blue line, but it will get really close, incredibly close, as x goes to infinity. So, thank you for watching. I hope you enjoyed the video. Please like, comment any feedback on the video, whether it's about the maths, other aspects of the video. Hit the subscribe button and the notification bell so you're notified of any future videos. Share with friends. There will be a second part of this video coming soon, and that'll be looking at limits. So we saw that as you increase the number of sides on this polygon, you get a much better approximation for pi. And also on radians, which is another form of angle measurement, and interestingly enough, it also involves pi, which is sort of related. Anyway, I hope you enjoyed, and bye-bye.